Okay, let's review lecture 21, quantum theory of metals. In this lecture, we talk about periodic boundary conditions first, and then we move on to talk about properties of electrons in a band, from which we derive the quantum theory of electric conduction in metals. Finally, we talk about electrons in the full band. So the first theorem outcome is that you should be able to describe the quantum mechanical behavior of an electron in a band, which includes the wave vector, momentum, and how they contribute to current with or without an external electrical field. So for a metal, we know that the band structure is described by a partially filled band, so that the Fermi energy runs through somewhere in the middle of the band. You have filled states and empty states in the same band. Now, with the periodic boundary condition, which is a bit different from the infinite potential well model that we talked about earlier, in which you have standing waves and then the dimension is a integer number of past waves. But now with the periodic boundary condition, we want to fill integer number of full waves in the system. So that gives you the wave vector being 2 pi over L times integer. And then this integer can be either positive or negative, accounting for waves propagating in either direction. And we know that the wave vector is associated with the momentum. So it's P is just h bar times k. And remember from classical physics, P is also mv. So in this case, the electronic states are equally spaced in the momentum axis or the wave vector axis. And then when we look at the contribution to electrical current, we know that moving charges give you a current, and so it's a velocity and charge get carried. But now in this system, under no electric field, then we always have states with equal number plus k and minus k states filling the electronic state. So in that case, when we have no electric field, the current density will be 0, no current at all. Things will be a bit different when we do apply electric field, because the electric field will cause electrostatic force on every electron that we have in the system. That will cause a change in the momentum or change in the wave vector. But this change is the same for everybody. And then for every electron filling those states, the corresponding wave vector will actually move toward the same direction. If the E field points from right to left, then delta K will be positive. This change will not go on forever because we have lattice scattering, so that will give you a mean free time. And then so with that scattering, eventually it reaches sort of a steady state. Now let's look at the contribution to electrical current. For electronic states way below the Fermi energy, you can still have this cancellation, plus k and minus k states cancel it out. But for states near the Fermi energy, they cannot be canceled out. Okay, so that's why in the end, the conductivity of the system is going to be dictated by how abundant those electronic states are near the Fermi energy. And then we have a net current, which is in the same direction as electric field. So next, the student learning outcome is to identify key parameters affecting the electric conductivity of metals based on the quantum theory. And then you should also be able to use this quantum theory to explain experimental observations on the conductivity of different metals. So earlier, when we talked about the classical Joule model, we see that the conductivity is proportional to the total concentration of these valence electrons. Essentially, all the valence electrons are treated the same. But now that we've learned the quantum theory, we know that the conductivity is proportional to the density of states at the Fermi energy. And only electrons near the Fermi energy actually contribute to the electric conductivity. Okay. But in both cases, we see there's a mean free time involved in those conductivity. So that means that the relaxation time, which is a temperature-dependent term, now we can actually use that to both the classical and quantum theory to explain the temperature dependence of conductivity in metals. Basically, lattice scattering reduces the mean free time at higher temperatures that will cause a reduction in conductivity. But now that we learned the quantum theory, we can use that to explain the observed differences in different metals. Copper versus zinc, for example. Copper has higher conductivity, but apparently it has fewer number of valence electrons than zinc. And this is just because that in the copper 4s band, which is partially filled, actually half filled, the Fermi energy will run through somewhere near the middle of the band. And in that case, we're going to have a very high density of states and very high electrical conductivity. In the case of zinc, the 4s band is nearly filled, but because the 4s band and the 4p band have some overlap in energy, the top of the 4s band will be empty and the bottom of the 4p band will be filled. So the Fermi energy actually is going to be very close to the top of the 4s band edge and then close to the bottom of the 4p band. So in that case, you have two pieces of dense substrates. Either one is not very big, so overall you still have appreciable conductivity in zinc, which is metal, but it's not going to be as high as in copper. Okay, so finally, you should also be able to explain why a full band has zero electrical conductivity. We have a partially filled band in most metals, and that's why we have these metals with very high electrical conductivity. The conductivity depends on, is determined by the dense substrates at Fermi energy. But if the band is entirely full and all states are occupied, then every time you have a change in the momentum or wave factor for those electrons due to the electric field you apply, essentially just create a permutation of all the electrons in that band. So the net result is zero. You have no net current and the conductivity is zero. This applies to the valence band of the semiconductor, which we're going to talk about in 2 lectures from now. Okay, this is the end of the review. Thank you.